Hello and welcome to another session. Hopefully I can make some sense out of something called the pH scale. I know that some of you might have heard something about that, but what I'm going to do is to go through and link what we already know with the pH scale so that we can extend our understanding. As always, if you're having trouble with this, we can listen to it again, or you can see your teacher. Or then again, you could always do both. So let's go back and see what we already know. In the lesson on acids, we learned that acids are all about hydrogen ions or H plus ions. And these things are present in the acid when they're in water. And we also said that we use a term called strong and weak in acids. And the term strong applies to acids where there are lots of H+. In weak acids, there aren't as many H+ in the water. So this makes it good for us to use. And I want you to think about that for a minute. But we use a special term to talk about the number of chemicals or the number of, we actually call them chemical species. So an ion would be one type of chemical species, and so we could talk about a concentration of how much that element is there or how much that ion is there. So I'm going to use the word concentration a bit this time. And not to leave bases and alkalis out, we decided that alkalis were all about making OH minus ions in water. Right? As we'll find out, this becomes really important when we do neutralisation. But more about that later. So let's concentrate more on the pH scale. We use the H+ concentration, or the amount of H+, to help us understand what's going on. Okay, so chemists have developed a scale that goes from 0 to 14. And 0 is strong acids, 0, 1, 2 strong acids, as you can see on our little scale up here. At the lower end, right lower end with strong, as we move closer to neutral, the acids become weaker. Alright? And then after that, the bases take over. So the pH scale allows us to check on the strength of an acid or the strength of a base. So it's really useful in that way. But it has its problems too. The problems are that it's only for acids that are dissolved in water. And luckily for us, that's the sort of acids we're going to be using in our classrooms. So it works really, really well for the acids we use in our classroom. Now down here, we saw in a video that we watched, one of our videos to look at, we've talked about the pH being the power of the hydrogen, or the power of H+, and I've mentioned that in its scale. Now notice that it's little p, big H. Most important, we write things as they're supposed to be written. It's not capital P, capital H, it's small p, capital H. Okay, please don't get it the other way. Alright, but there's one thing we need to know. The scale's not like a ruler. It doesn't go up in equal increments. Alright, so I need you to think about this. It's not like it's a linear scale. It's a special scale which we call a logarithmic scale. And that means things move up 10 times. So as I've said here, a change of 1, so if something moves from pH 1 to pH 2, it's a 10 times change. Alright? So if we go pH to pH 2, it's a 10 times change. Different. We look and see 1 on the scale, but really we're talking in tens. So if we do it for pH 1 to pH 3, then we have got a 1 and a 1 again. Now if it's 1, if every time we change by 1 it goes up by 10, then it's not 10 plus 10, it'll be 10 times 10, so the change is actually 100 times. Now the changes we're talking about are in the hydrogen ion concentration and to a lesser degree in the hydroxide ion concentration. So a pH of changing from 1 to 4, so we've moved 3 spots, so it's 10 times 10 times 10, so it's actually a difference of 1,000 times in the concentration. So in other words, a pH 4, the concentration of hydrogen ions is 1,000th that it was in pH 1. That's a lot. That's a heck of a lot. So how about we combine all that in the end? Here I've tried to combine it. I've got our picture over here which we had to start off with, which has got strong and weak acids. Now I put in here about H pluses. Now there are always H pluses and OH minuses in the water. Okay, they're always going to be there. It's just that we're talking about the amounts. Now in the very low pHs over here where it's strong acids, there are huge amounts of H pluses, but not much OH minuses. So the H pluses really overpower the OH minuses, and we have a strong acid. When we get to the neutral situation, believe it or not, at exactly 7, the H plus and OH minus are going to be the same. They're going to be equal to each other. Yeah? And last, if we go to a strong base doesn't mean we don't have any H pluses, but like we saw for strong acids, the amount of OH minuses in a strong base is huge. The amount of H pluses is very, very tiny. So the OH minuses overpower. And because there's so many of them, we don't measure a very high concentration of H pluses. So we can see that this pH scale is useful because it allows us to see if something's a strong or a weak acid or a strong or a weak base by its position on the pH scale. And then we can also see that it's related to the amount of H pluses on the scale. Alright, the H pluses start off very, very high at low pHs and become very, very low at high pHs. The concentration of OH minuses is reversed. It starts off very, very low at low pHs and becomes very, very high at high pHs. I hope that has made a little bit of sense about the pH scale. Now we do mention pH in other things, and soon we'll look at what happens when acids and bases mix together. And on that, I think it's time to say goodbye today.